You're watching a Channel 98 NBISD TV production.
Hello out there in TV land. Welcome to Deja Vu. It's Algebra 2. As always, I'm your host, Kevin Corpy. Today we're going to be talking about rational functions. Now, if you've watched the last couple of episodes, we've been looking at rational expressions. We multiplied and divided them on one show. The next show, the last show, we added and subtracted them. Well, today we're going to be looking at rational functions, which is just a function that it has a rational expression in it. And we're going to be interested in the graphs of these rational functions. So, it's a show that you're definitely not going to want to miss. Download the worksheets from the district website, grab a sharp pointy pencil, and stick around for about 30 minutes or so and learn a little about rational functions with me today. Okay, lesson 23, rational functions. What is a rational function? I know you're asking yourself that. Well, a rational function is nothing more than a function, first of all, that has an equal sign. Okay, so it's f of x equals, and what it equals is a rational expression. Okay, so it's basically a rational expression that's said equal to y, or f of x. And remember, rational expression is just the quotient of two polynomials. Now, some rational functions can be graphed as transformations of a very common scaled-down rational function called 1 over x, the reciprocal function. And here's what reciprocal function 1 over x looks like. We are going to be looking at the graphs of these rational functions today. So you could think of this as a parent function. And transformations now are going to be transformations of this parent function. So it's just 1 over x. Now, of course, we know that x cannot equal 0. So if we're looking at the graph of this, being curious-minded students, if I told you don't use 0, don't go to 0, then graphically you might be saying, if we can't go to 0, what does the graph look like at 0? Very good question. Well, the graph looks like this. Ta-da, there it is. It's actually a hyperbola that's rotated 45 degrees. A hyperbola is going to come up later in the year when we talk about conics. But notice that since x cannot equal 0, we have this imaginary line drawn in here that's called a vertical asymptote, okay, at x equals 0. Now also notice that as we are coming in from the left, the y values are negative. Okay, when x is negative, y is negative, because the reciprocal of a negative number is negative. And it comes down and it goes down very rapidly, approaching this vertical asymptote. And then, on the other side of 0, when x is positive, it jumps way up here. And it comes down and decreases very rapidly. So why is that? Well, if you think of this as just being the reciprocal function, take a number that's just larger than 0, like 1 over 1,000. Well, what's the reciprocal of 1 over 1,000? It's 1,000, which is very tall. As we get closer, 1/2, the reciprocal of 1/2 is 2. The reciprocal of 1 is 1. The reciprocal of 2 is 1/2. The reciprocal of 3 is 1/3, so on and so forth. So it appears that this graph is coming from a vertical asymptote and now approaching a horizontal asymptote. They never actually touch the asymptote. Okay? Now that's a very important feature of this graph. Let's go ahead and say that it has a vertical asymptote. Here's how you spell it. Asymptote. There you go. At x equals 0. And I'm going to call vertical asymptotes VA from now on, vertical asymptote. And we also have a horizontal asymptote. Same word, which I will call those HAs. And we have that on the x-axis, which is also known as y equals 0. Now, asymptotes are going to be kind of like gravity. The graph is going to be gently drawn towards them. And although it's nice to draw these lines in here for reference, they're not actually part of the graph. Now, what can we say about this function other than that? Well, what's the domain? The domain is going to be everything except x equaling 0. And what's the range? The range is the set of y values. What y values do we take on? Well, we take on all these negative values except 0. That's what the horizontal asymptote is. So both the domain and range are going to be all values except 0. Now, once we have that, we can talk about transformations of this function 1 over x, which is the reciprocal parent function that is also a rational function. Okay, now transformations of functions in general is going to be a hugely important concept. And we've already talked about it earlier this year when we talked about parabolas. When you go on to take pre-calculus and calculus, transformations are going to be just a part of everyday living in the math class. So what we're going to do now is we're going to review some basic transformations specifically for the function 1 over x. If I look at this general form, You see 1 over x. It's a reciprocal function. There it is. But instead of a 1, I have an a. I'm multiplying the entire function by a. That's going to be a vertical dilation factor. Okay? The c, remember, is being added and subtracted to the x, which is the horizontal component. This is going to be a horizontal shift, left or right. The plus d is what's being added to the function, which is the y value, almost as an afterthought. So that's going to take all your y values and raise them by d or lower them by d. Now, what's interesting to note is how that affects the graph. Because we have a vertical asymptote, the only type of thing that's going to change the location of my vertical asymptote is a horizontal shift, which is c. So we know that we're going to have a vertical asymptote, or a VA now, at x equals c, and that's going to be the value that makes the denominator 0. If you plug in a c for x, you get c minus c, which is 0. That's a vertical asymptote. We know also that the only thing that's going to move our horizontal asymptote is a vertical shift, and that's going to be our d. So we're going to have an HA, a horizontal asymptote, at y equals d. Now, if a is positive, it's just going to stretch the graph vertically by that factor or compress it. If a is negative, all your y values now are going to interchange like this, which is going to be an x-axis reflection, remember. Okay, let's put that to good use. Let's look at this example. It's g of x. We have g of x equals negative 1 over x plus 3 minus 2. What we want to do is state the domain and range and list the asymptotes. Well, the domain is going to be easy to find without the graph because there's really only one thing we're worried about when we have rational functions, division by 0. So any variables in the denominator that give us a 0 when we plug in are off limits. So when I plug in a negative 3 here, negative 3 plus 3 gives me a 0. So the domain is going to be the set of all x's such that x is not equal to negative 3. Easy from the equation, can't divide by 0. The range is not going to be as easy to get from the equation, but it will be once we have the graph. So let's go ahead and do that. Well, notice that in this case, if I fit it to this pattern, my a is negative 1. So let's go ahead and list that. A is negative 1. This is x plus 3, which is really x minus negative 3. So my c value is really negative 3. If you wanted to write that as x minus negative 3, that's fine. This minus 2 is really like our plus d. So d is going to be negative 2. So what this really does to our parent function is it moves it left 3, it moves it down 2, and it reflects it across the x-axis. Now, if you can sketch your vertical and horizontal asymptotes first, that defines the behavior of the graph because they are like gravity. The graph is going to be drawn towards them. So let's go ahead and do that. I draw my little axis here, and I know it's going to be left 3, so that my vertical asymptote is right there. And if we're drawing it by hand, we'll just draw it as a dotted vertical line. And I know everything's moved down 2, so 1, 2 units, and I draw my horizontal asymptote. Now remember, the parent function lives basically up and to the right and down and to the left in those quadrants. But if you have a negative, it's going to reflect it across the y-axis. So this graph here will reflect down into this region, and this branch here will reflect up there. So this is my basic shape now, and again, I draw it depending on the vertical and horizontal asymptotes. So I'll draw it down here, and then I'll draw the other branch up here. And now we have the graph right there by hand, just using some basic information on transformations. Well, notice now in this graph that the domain can't equal the vertical asymptote. But what's the range? Well, we have all the negative y values approaching this number here, which is negative 2. And then over here we pick up just above negative 2 and go up to infinity. So the range, R, is going to be the set of all y's except the one where we have the horizontal asymptote. There you go. And I'll go ahead and list it. We have a VA at x equals negative 3. That's the value of x that we're not allowed to use. And we have a horizontal asymptote, an HA, at y equals negative 2. That's our value of d, remember. Okay? It's worth memorizing this pattern and what they do to the graphs. But if you know how they affect the graphs and you memorize what the parent function looks like, then you'll know exactly where the vertical and horizontal asymptote go. So memorize it. Okay, so if we look at the graph of g of x on the calculator, we type it into y1 and we graph it in a window. Zoom 4, by the way, is a good window to do whenever you're going to have vertical asymptotes because it's a decimal window, and very often you will not see the calculator trying to graph that vertical line. And I'll show you what I mean here in just a second. But this right here, if you hit Zoom 4 and you adjust your window, what I did is I multiplied my window on a zoom 4 would be negative 3.1 to 3.1. I multiplied that by 3, so I was negative 9.3 to 9.3, and then the x window was okay. So we get this graph. Now, according to this graph, we can kind of see that there's a vertical asymptote right in here. That would be that imaginary vertical line running right through here, and that would be at x equals negative 3. And we also said there was a horizontal asymptote at y equals negative 2. And if we drew a horizontal line right through y equals negative 2, you can kind of see that the graphs are kind of like it's tapering off as we go off this way to the right towards the horizontal asymptote. And as it comes down here on the left, it approaches the horizontal asymptote from above. So the way that the two branches of this curve kind of curve away from each other kind of implies that there's some hidden force like gravity. And those are the asymptotes. Asymptotes are really like gravity when it comes to equations. The graph is going to be gently drawn towards them in the long run. Okay? And therefore the domain we can clearly see is all the x values except the ones at the vertical asymptote at negative 3. And the range is going to be all the y values except all the ones down at negative 2. Now let me show you what I mean about graphing in a standard viewing when most times we graph it in a negative 10 to negative 10 on the x and y axis, which is a zoom 6. We're going to get the same graph, but notice that it looks like a heartbeat graph. The graph goes up and then bloop, it blips down and goes like this. That vertical line, your calculator is a function graphing machine. It tries to connect the values, but it goes so steeply up coming in from the left and rises so steeply coming in from the bottom there because of the vertical asymptote that your calculator's pixel resolution does not allow it to draw it infinitely close to the vertical asymptote. So it gets to a point where it says, I'm close enough, and it calls that a point, and then it picks back up at the bottom. And it connects the dot because it's graphing it from left to right. So if you graph it in a decimal, zoom 4, it assigns basically every value on the pixel screen to an integer value of x, and so you don't see the vertical asymptote. Another way to do it if you don't want to do the zoom 4, because you do have to play with the multiples of the x and y scale there, is you could do this. You can go to your mode, and instead of going connected mode down there, you can graph it in dot mode. And what that does is it actually plots the points that the calculator does before it connects them, and then it doesn't connect them at all. Now you don't see the entire graph, but notice that this last point right here, and this is the last point it calculates here, it doesn't connect the dots anymore. And you can kind of infer that it goes up and goes down on either side, okay, like this. There we go. All right. All right. So there you go. Zoom 4 is nice, but it's not necessary as long as you realize the heartbeat is not part of the graph. It's a vertical asymptote. All right. Time for a real quick break. Watch some public service announcements. And while you're gone, think about this. What did one eye say to the other eye? The answer when you get back.
My cell phone number and John's cell phone number. Hey, pretty. And number of the restaurant where we're going to be. And oh, I've left you my pager number too, just in case, because you never know. John, you have the gift?
The odds of a babysitter calling 911, 1 in 1,400.
So if anything should happen, please don't hesitate.
The odds of a child being diagnosed with autism, 1 in 150. You know the odds of autism. Now learn the signs. Go to autismspeaks.org.
Yesterday, my friends told me to smoke some pot, and I did. Then today, they said I should try and fit my fist into my mouth. It fits, but I can't get it out. I'm an idiot. I'm under the influence of others, and that ain't me. That's what he said.
Live above the influence. Above them, above weed.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy. Today, talking to you about rational functions. Did you think about what one eye said to the other eye? Here's what it said. It said, between you and me, something smells. Yeah, I smell a bad joke. But I also smell math. Let's get back to the math. Yeah. Okay, as you saw, that previous graph had a discontinuity. Now, a discontinuity is kind of exactly what it implies. You try to think of continuity as sketching the graph from left to right, okay, in a nice, smooth, even fashion. Anything that's going to cause you to lift your pen or pencil or your dry erase marker or whatever it is you're using to draw this, anything that causes you to lift that is going to be a break in the graph. It's going to be a discontinuity. And the vertical asymptote in the last one was a discontinuity. I have to actually lift my pencil and then pick it up and continue drawing on the other side. Now, rational functions have two types of discontinuities. They do have the type we just saw, the vertical asymptote, which I saw, or I write as a VA. It's an infinite type of discontinuity because as the graph approaches a vertical asymptote, it's like gravity. There's only two things it could do. It'll curve up and go to positive infinity, or it'll curve down and go to negative infinity. That's it. It's not like a semi-permeable membrane where it can sneak through. It doesn't cut across. It goes down to infinity as it gets closer and closer to it, or it goes up to infinity as it gets closer and closer. At any case, you have to lift your pen or pencil. And remember, those were the values that made the denominator 0. Now there's another type, a removable discontinuity, or a hole. A hole in the graph is also something that's going to require you to lift your pen or pencil. You have to stop, get over the other side of the hole, and continue going. Now, what you're going to be responsible for is identifying just from the equation what makes a vertical asymptote versus what makes a hole, which is basically a point discontinuity. It's like we swipe a single point out of the graph. Okay? Here's how you know. A removable or a point discontinuity is going to be a value that makes both the numerator and the denominator 0. 0 over 0 when you plug in is a hole. It's a removable discontinuity. As you're going to see, you're going to be able to factor and remove that factor that's causing the 0 over 0. And because you can remove it from the equation, you're going to be able to remove that point from the graph. So 0 over 0 is a hole, and you can remove the factor. Two ways to remember removable discontinuity. It's another type. So let's look at this equation right here. We're going to want to graph it, and we're going to talk about it extensively. It is a rational function, p of x, and what we want to do when we're analyzing domain and range and all that stuff, trying to graph it, we want to factor it as much as we can. So the numerator is x minus 3. I can pull out a common factor of x, and that leaves x plus 2 all over the bottom, which is x times x plus 1. Now before you cancel anything out, ask yourself this. What values make the denominator 0? What are the two roots of the denominator? Well, 0, x cannot equal 0, and negative 1. X cannot equal negative 1. Those two values right there are going to be discontinuities. We cannot divide by 0, so they're going to break the flow of the graph. Now, the question is it a vertical asymptote or is it a hole? Well, notice over here I have an x factor and an x factor. If I plugged in a 0 into the numerator, I'm going to get 0 over 0 because of that factor. 0 over 0 means a hole. Also, I can remove the factor of x from the equation, which means I can remove that point from the graph. So there's two indications that we are going to have a hole at x equals 0. We don't know really what the y value is yet. You'll learn that in pre-cal or calculus. But we do know at x equals 0, there's a hole. It's just a single point taken out of the graph at x equals 0. Now notice that the other factor, x plus 1, it remains. We cannot divide it out. If you plug the negative 1 in the numerator, you get negative 4 times 1 over 0. That's a non-zero over 0. In other words, negative 1 only makes the denominator 0, not the numerator. That's a clear sign that it's a vertical asymptote. So we have a VA at x equals negative 1. And those are the two discontinuities. Now also notice in this case, what remains is really all that's important. This is not going to be a transformation of 1 over x. So what we're going to have to do is figure out another way to graph it. Well, what I can do before I start is I can get my vertical asymptote going. I know it's right here at negative 1. And we're going to have to figure out some other things about this. Well, another thing that we can look at are the x-intercepts. Now, the x-intercepts are the values that make the entire function 0. Now, when is a fraction equal to 0? A fraction is equal to 0 when the numerator is equal to 0. And the numerator is equal to 0 when x is 3 and x is negative 2. Notice we already got rid of the hole. X did make the numerator 0, but it's a hole. And you can't have an x-intercept, a point where it crosses the x-axis, as a hole. So you need to get rid of the removable discontinuities or the holes first. Any value that remains that makes the numerator 0 is an x-intercept. So we got x equals 3 and x equals negative 2. We can actually plot those. 1, 2, 3. There is an x-intercept. And x equals negative 2. 1, 2. So we know it crosses there. We know that wherever x is 0, we have a hole. But what does the rest of the graph look like? Well, for that, we're going to go to the calculator. Here's the graph of p of x on the calculator. Again, I graphed it in the zoom decimal window, and I stretched my vertical axis by a factor of 3. Now, we want to verify that we had a vertical asymptote at negative 1 and a hole at x equals 0. Well, if you notice the way these curves, as we come in from the right, it's going down very rapidly, and as we come in from the left, it's going up very rapidly. So again, there's that hidden force that the graph is kind of like drawn to. that implies a vertical asymptote. And we decided on the calculator, or by hand, sorry, that it was at -1, x equals -1. And on the calculator, you can see if you drew this imaginary vertical line running right here through -1, those lines of the graph would actually be approaching it. We also said that there was a hole at x equals 0. Well, x equals 0 is right here on the y-axis. Now notice the graph is not merging towards x equals 0. In this case, it's just like passing right through x equals 0. Here's x equals 0, and the graph exists to the left or to the right. So that's a difference in that continuity. It's not an asymptote. The graph's not going to be drawn towards it. It's a point discontinuity. It's like someone just came through and wiped out a single point out of the graph. Now, why don't we see a hole? Well, for a couple reasons. If you're not graphed in a zoom decimal window, you probably won't see the hole because the calculator will graph right over it. But in zoom 4, you should see it. Now, because this hole happens to be on the y-axis, the axis itself is kind of plugging the hole. So we could turn the axis off this way. If we hit second zoom, which is our format, we can go down here to axis off. And I'll hit enter. And now if I hit graph, it'll graph the exact same thing. You see how the graph curved up? And now notice right here, you could see that little bitty gap right there. That's the hole. That's the removable point discontinuity at x equals 0. So a vertical asymptote is a discontinuity. We have to pick up our pencil. And the hole is a type of discontinuity. We have to pick up our pencil. But two different types. And they come from two different things in the equation. And you have to know both. All right, there's another important aspect that we're not going to get to today on the show because we're running out of time. And that is basically how to identify a horizontal asymptote from the equation. Horizontal asymptotes are not discontinuities. They do not cause you to lift your pen or pencil up. Think about it as running along a shoreline. You're not trying to cross the river, a horizontal asymptote. Okay? But there is a way to find it. There's basically three cases, and you're analyzing the degrees of the numerators and the denominators. And I have a handout printed if you want to download them online, or ask your teacher about it. But again, there's three cases. You should memorize each of the three cases, and that'll tell you how to find the horizontal asymptotes. Okay? Now we're going to move on to my favorite part of the show.
Deja Review.
All right, and for this we're going to take a band trip. What we're doing here is we've got a high school band. It could be New Braunfels High School. Yay, go band. There's a great band. Let's say they were so good they were invited to play at a college bowl game. Okay? With the Unicorn Band, I wouldn't doubt that's possible. But it costs money to go. So the trip is going to cost each student $500 plus a $2,000 deposit for the whole band. Now what we want to do is we want to write a function that represents the average cost of the entire trip per student. Okay? The average cost per student. So here's what we're going to do. We're going to write the function as c of x. If it costs each student $500 per student, then the average cost is going to be 500 per student plus the more students we have, the more we're going to be able to offset that 2,000 deposit. So I could say 2,000 divided by x, where x is the number of students that attend. And then c of x is going to be the average cost. So every student has to pay $500. There's no getting around that. But as x increases, the number of students that increase, the cost per student on that $2,000 decreases. Okay? Now this is a rational function. And notice that it is a transformation of our parent function 1 over x. If I rewrite that, I get 2,000 over x plus 500. And this is of the form a over c plus d. Well, a is 2,000, c is nothing. We don't have a horizontal shift. D is 500. So remember, that was the horizontal asymptote. So if we want to graph this in a relevant domain, we're going to go ahead and graph it right here. There's the horizontal asymptote at y equals 500. We have a vertical asymptote at 0. And remember that the function, since there's no reflection, lives up there. Now this is a relevant domain. We have a vertical asymptote at 0, horizontal asymptote at 500. We're not interested in negative people going. We're not interested in negative costs. So there's the graph. Let's go to the calculator and check it out there. Okay, what I have graphed here is the average cost per student function, which we called c of x. That's what I put into y1. And so now we're not just talking about x's and y's. We're talking about the average cost per student on the y-axis, and x is the number of students that plan on going on the trip. So in this case, we need a relevant domain. So the relevant domain, again, is we have to look at values of x greater than or equal to 0. We can't have negative students going on the trip. So I set my lower bound to 0. That's if nobody goes. And my upper bound, I just set it at 100. If we needed to go further out, we definitely could. The cost, what's the y, the range? Well, 0 would be the lower bound. It's not going to cost people negative dollars. What's the maximum cost? Well, if it costs the school a $2,000 one-time fee plus $500 per person, then if one person goes, it'd be silly if nobody went. If one person went, that'd be $2,000 plus $500. So $2,500 could be an upper bound, 0 could be a lower bound in the context of this problem, even though the actual domain and range of the function itself could be different. So now that we know that, there is a vertical asymptote right here at x equals 0, which is the y-axis, and notice the curve goes up very rapidly. And there is also a horizontal asymptote. Notice as we come down from the right, these y values taper off. They're decreasing, but they're not decreasing down to negative infinity. They're decreasing approaching the horizontal asymptote, which is in fact $500. So in the context of this problem, as x, the number of students who go on the trip, increases, the average cost per student decreases. And that makes sense because among themselves, they are splitting the $2,000 fee. And so if thousands and thousands of people went, that $2,000 can be absorbed to just fractions of cents for everybody. And so effectively each student is paying $500 plus maybe a penny or something like that. So it makes sense that the average cost per student is going to be approaching $500 as more and more students sign up. But if we want to know what the average cost is for 50 students, well, that's just plugging in a 50 for x. And I can hit the trace button and punch 50, which is right here, hit enter, and I get 540. That means if 50 students go on this trip, it's going to cost each of them $540. Okay? You can also plug it by hand and get the same number, but it's nice to use the calculator when we have a graph in a relevant window, which is important. Okay, rational functions, very important types of functions. Lots of things can be modeled with rational functions, but they are kind of tricky because of those asymptotes. One's a vertical asymptote and it's a discontinuity. One's a horizontal asymptote, but it's not a discontinuity. And then we got these holes, okay? There's a lot of new terminology that you need to know. And again, there's no magical secret other than memorize the definitions and then put it into practice and practice, practice, practice. Work a lot of problems. You'll get used to it and you'll get good at doing it as well. Now we are out of time for this week, so I hope that you had a good time. And I also hope that you join me next week for another fantastic episode of Deja Vu, It's Algebra 2. Until then, though, I am Kevin Corpy reminding you to do your homework.